welcome everybody to our December public night. The first of three that we do on Zoom only during the winter month where the observatory is closed to the public. If you would like access to the observatory, make sure to become a member. There are so many other perks that, I always talk about when, in our public nights. We do have our next member meeting is on Saturday, December 9th. And yes, we are having pizza. Um, Carl, you want to take it from here and introduce our speaker?
Group. So without any further words from Carl, welcome Scott McIntosh to CAA December presentation. Looking forward to hearing your presentation about Cycle 25.
Yeah, and thanks, Carl. And you booked me up a long time ago, almost so long ago that I almost forgot. So it was in the dark depths of my calendar, and I dug it out. So
thank you.
And also, I have a weird background. So other than being Scottish, there's other weirdness. So my background's actually I'm a medical physicist by way back. So I actually stumbled into astronomy and astrophysics by complete accident. So.
Wow.
So yeah, I was brought into a PhD project to do a kind of tomographic study of the sun. Wow. Because of the math, because we did the same math and physics, yes. But the idea was to use it on an optically thin ultraviolet emitting plasma instead, right? So we have one of those on our doorstep. Well, 93 million miles away, but other than that. And I got kind of trapped. So 20-something years later, this is like, actually, what I'm going to show you is about the culmination of 22 years of work. Well, actually, not quite the culmination because we're still going. So yeah, I feel old when I talk about that. In 3 days, it will be the 26th anniversary of me getting my PhD. Now I feel really old. But there's a little bit of Doogie Howser in there. So I was pretty young because most Brits are when they get their PhDs. So, because we don't have to go through all the grad school torture. So, anyway, so I'm going to start if you don't mind. I'll share my screen here. Let me know if you can see that. All right, and I'll turn it into, and I think I'm still visible. All right, so this is a fun movie from about 10 months ago. And it generated quite a lot of interest because basically it looks like someone's toupee is flying off the top of the sun, right? Yeah. And the idea is that, and we'll get to this in a little bit, but the structure wobbles, rotates, and does all kinds of things at the same time, right? And one of the challenges with being a solar physicist is to try and interpret the waves and things that you see in the context of what does that tell me about the plasma or the atmosphere of the star. And for me, it's actually about what's it telling me about what's going on back out of view. So what's going on the inside, right? So a lot of this talk, while it's looking at features that manifest on the outside of the sun, the idea is to have them help me understand what's going on in the inside, right? So anyway, I have 35 slides. I have been known to do this in about 30 minutes. I have also been known to do this in about 75, okay? So it just depends. So get your coffee cup filled or your beverage of choice. We'll start, okay? So thanks, Carl, for inviting me.
Thank you.
And this is kind of a prelude and a preface to this work. So I'm going to cover where we were 20-something years ago. But cycle 25 for the present sunspot cycle presented an opportunity to us. There's a really rather sneaky article in Science magazine that was published in maybe late 2019. And if you're really interested, I can point you to the link. It portrays me as a kind of Darth Vader kind of character. But, at my office, the panel that was meeting to predict sunspot cycle 25 was meeting. Okay. I was unfortunately wrapped up in all kinds of strategic planning meetings, so I couldn't participate. One of my colleagues participated, however. And right about the same time, we made, like, literally that week, we made a bit of a discovery. And the bit of a discovery we made was that Cycle 25 wasn't going to do what the experts in the field were saying it was going to do. And so foolishly, whatever rhymes with bullshit, we decided that, this is actually an opportunity. We think the sun works differently from the way the current generation of models would imply that it does. And so this very stark contrast between our forecast in red and their forecast in blue presents a rather nice opportunity to demonstrate, well, are you right or are you wrong? There's not, for many of you that are scientists, there's not a lot of accountability in science. So you can be glaringly wrong and just restart and do it again, right? So we thought that since if you hit the Google machine and input solar dynamo or sunspot cycle, how does it work? Invariably, you get the same output.
Yep.
You get linked to the same movie, the same narrative, the same story. We're not sure that that's right. Okay, so Sunspot Cycle 25 presents as an opportunity to verify that. Here's going back, to the very early phases of what's going on. And even in the early days of 2021, things were starting to deviate, right?
A lot.
So again, red and blue, right? It was already trending away. Okay. We'll get to this in a minute, even if you time shifted all the data, right? So there's all kinds of shenanigans going on, right? So anyway, I'm putting those movies back in because I thought it was pretty active. This time last year, this thing called the polar crown filament. Those of you probably observe filaments and prominences through your H-alpha telescopes. There's probably not much of a polar crown filament visible anymore, but about a year ago was the optimal time to see it about 65 degrees latitude. There's a funny story to that too. Maybe I'll get to that a little bit later. But you should ask yourself, why the hell does a star have a polar crown filament? That's an important question, right? But because the magnetic flux is constantly changing, it becomes unstable and erupts just like this. Okay, so I'm not going, these are just eye candy. This is octal diabetes, as I call it, right? So just trying to overload you with sugar before we start the dirty work. So, $64 billion question, or it's actually probably more like a $1 or $2 billion question. How does the sun's internal magnetic machine work, right? The sun is a magnetic star. Not all stars are magnetic. Not all stars are active, but the one sitting, the rather benign teenaged one sitting on our doorstep, is a magnetically active star with a cycle, with a sunspot or activity cycle of the order of about 11 and a bit years. Let's now get into the orbital period of Jupiter, which is also about 11 and a bit years. But, we can have that question later on because it always comes up. But the idea is, how do you explain the magnetic field that's manifesting through the sun's surface as a function of space and time? But what you've got to really figure out is what we're seeing in this movie. If I play it again,
Yeah, there it is.
if it'll allow me to play it again, is the tip of the iceberg, right? So we all know that icebergs are 90% under the water. What is hidden from view is the big question. So back to my formative years when I had far more hair and a much better attitude, right? I had a supervisor, a guy called Joe Gurman, who's like a hero of solar physics. Okay, he's one of my heroes anyway. And I was an instrument scientist for a spacecraft called SOHO. Some of you may have heard of it. I learned to run 4 of the instruments on SOHO, and so as a young postdoc, they let young postdocs loose with the scientific planning for these instruments as a way of cutting our teeth on things and cheap labor, probably. But other than that, Joe Gurman came up to me one day when I was calibrating our telescope, which didn't take these images, but one's very much like it. And he said, you see those little bright features on the sun? I was like, yeah. I was like, you should write a little piece of code and analyze those coronal images. So this image is about 1,000,000 degrees, 1.5 million degrees plasma, and track them. See what you find. You might find something interesting. I was like, you're barking mad, Joe. But yeah, since you're my boss and you sign my check, I will go ahead and do that. So the sun has about somewhere between 400 and 600 of these things on the sun-Earth face at any moment in time. Okay, so the left-hand side is the raw image. The right-hand side is my little algorithm that goes in and finds these bright features by looking at contrast. Basically, very simple analysis, right? But you can imagine that telescope took 100 images a day. Starting in 2010, we had a satellite called the Solar Dynamics Observatory, which takes 7,200 images a day. Okay. So pretty soon you're getting to the biggest astronomical database in existence. So do the math, 400 or 500 times 100 or times 7,200 times 24 times 12. Yeah, you can do the math, right? It's a lot of things. You're in the billions, or maybe close to the trillions at this point. I should actually figure that out. So lots of objects. In the fall of 2012, so some 10 years after I started this exercise, there's a very renowned Earth system scientist called Maura Hagen that works at my old lab. She was actually the deputy director at the time. And I stumbled across something very unusual. And what I was looking at was the correspondence between the progression of these ultraviolet bright points as a function of latitude and time. And I noticed something really weird. So if you look at the focus your energy on the bottom right-hand side of that plot, give it away. Do you see how there's stuff at the equator, then all of a sudden it just disappears? Do you see it? Yeah. So what I mean is it goes from having color and it's just a dark blue black. Like it just goes. So it was very odd. Well, it was even more odd when it was clear that sunspots started emerging when that thing happened. Right? So sunspots are emerging at middle latitudes on the sun when this event at the equator happens. I was like, that's really bizarre. So I started looking at more and more data. I had shingles twice in the space of 18 months. Looked at something like 40 terabytes of data, Carl, in that time frame, right? From all kinds of sources. And this is the picture. This is a series of slides that I gave to Maura Hagen in 2012 to present to the National Science Foundation, right? And what I noticed was there was significant overlap in space and time of these bands. And in fact, if you look, solar minimum here, the time where the sun makes no sunspots in 2008, there's very clearly 4 systems present. There's 4 bands, 2 at mid-latitudes and 2 near the equator.
You can see it.
And in the kind of canonical picture of sunspots, that kind of doesn't work. Okay? So I'm already starting to think that there's something weird going on. There's like a trail of breadcrumbs, if you like. So I started trying to follow it. And so I started trying to follow it in a different set of diagnostics. So this is from the same slide deck in 2012. Okay? At the time, I was writing a paper for Science magazine on this. Anybody who wants to read that paper, it's probably as dense as a neutron star, right? It never got accepted, right? But what we basically identified was that the progression of these little bright point things was linear, at least to the best we could tell. And also that this event near the equator, which we subsequently called the Terminator event,
yes,
is somehow very much a part and parcel of the sunspot cycle switching on and off. Okay? And so on this plot, my then 2012, my then 5-year-old drew straight lines for me. Okay. Because, I'm a bit of a cantankerous bugger. So I wanted to make sure that, just to emphasize the point, that it was pretty straight. I had my 5-year-old draw the straight line. Well, the ones in red that you see are what I expect to happen over the next, well, many years, 10 years. And the ones in magenta, you see those magenta ones?
Yeah.
Those are not purely speculative. Those are based on the 40 terabytes of historical data analysis. So what we basically discovered was that the sun's underlying magnetic cycle repeats itself every 21.8 years. And it starts, or appears to start, at about 55 degrees latitude. This is where the polar crown filament story will come in later on, right? So do you want to see how that progressed with time?
Yeah.
Oh, that's not bad.
Wow. Right on your line.
Okay, so jumping 5 years further in the future, how are we doing? Was the question in 2017. Okay. So the idea was that this is a predictive tool. So in principle, we can tell when the next Terminator event's going to happen, maybe. But that means we can also tell when the sunspots of sunspot cycle 25 are going to take off, right? So this is the start of being murky, okay? So stepping back a little bit, and this is a little bit more recent graphics. Here's the hemispheric sunspot number. So in black is the total number. Red and blue are the two hemispheres. There's a whole 2-hour-long presentation on why they wiggle. Can you see the wiggles?
Yeah.
Those wiggles are to do with Rossby modes on the inside of the sun. Rossby modes are atmospheric or planetary scale waves, right? And it turns out that a lot of space weather is intrinsically tied to these waves. So weather on the sun is analogous to weather on the Earth. So, but we won't get into that because that's a whole different topic.
That's another presentation.
But what we basically noticed was that when we finally get through this paper, was that someone in 1988 had basically discovered the same thing. And they called it the extended solar cycle. And what that basically means is that the butterfly diagram that you're probably, at least some of you are familiar with, if you turn your head to the side, you can see that it looks like butterfly wings if you stack up lots of cycles. Well, it turns out that the wings of the butterfly are extended back in time and up in latitude. That's the work that they did. And it looks kind of like this red, white, and blue thing here. Yeah. Okay. But on top of that, I've superimposed magnetic polarities. So positive and negative. And each repetition of that is what they call a Hale cycle, or a sun's magnetic activity cycle. If you pay close attention to this curve on the upper left-hand side, so those green dots, see the green dots here? If I go up, can you see my arrow, my cursor?
Yeah, yes, we can.
Do you see that tracing that out?
Yes.
So things like magnetic filaments trace neutral lines in the magnetic field. So when you see a filament, it means that the magnetic field is probably zero there, right? It finds global minima. And so what you see here, so this wasn't designed to do this, but you see how beautifully those filaments, so this is just mapping on a plot as a function of latitude where the filaments are on the disk. See how beautifully it traces that?
Yeah.
But furthermore, see how they really want to sit at 55 degrees latitude? For a long, long time. That's a bloody mystery, right? So, but anyway, this is just a kind of graphic illustrating the Hale cycle. So I'm jumping forward a good number of years now. This is an infographic that I built for an article that featured in one of the ham radio magazines trying to explain this stuff, right? One of the things that's important to understand is focus your eyes again back on 2008. 2008, 2009 is the middle of the solar minimum between 23 and 24. And what we're basically saying is during sunspot minimum, there are 4 oppositely polarized magnetic bands around the sun's equator. What does that mean? It means that they're probably canceling each other out. Right? So the net field is close to zero. but not locally, right? There's strong field locally, but the net field is close to zero. When those bands come in and pinch off at the equator, you generate imbalance or asymmetry in the field again. And then, boom, you get the switch on of the sunspots, right? So you have this progression between 2 magnetic bands in the ascending phase and 4 in the declining phase, and then it repeats itself again and again and again and again. Okay, so this is the basic precept, but sunspot minimum is the key to it all. So when you're trying to explain this to anyone, you go, well, I've got 4 magnetic systems. 2 years later, there's only 2, and then I see growth. So what's going on? Why is this controversial? It's controversial because in the paradigm-defining models of sunspot activity, where the sunspots come from, the magnetic fields are passive, right? They're tracers of the flow inside the sun. This would appear to contradict that 180 degrees, right? That the magnetic fields know about one another, and they're important to the puzzle. They're not just passive tracers, right? And this may sound like nuance, but it may be a lot more than nuance, a lot less than nuance, I guess, whatever way you want to look at it. But this is a schematic to kind of hold in your head. And so whatever happens at 55 degrees latitude, there's a new cycle band created, and it starts to propagate from that latitude down. And again, you see as we progress towards 2020, we're projecting the cycle 25 bands. And yes, in the next year or so, we will see the cycle 26 bands, right? And we can trace them back to their very origins at 55 degrees latitude. Okay? So again, you'll see this plot over and over again. In this plot, you'll see this beautifully defined Terminator event in 2011. Yeah. If I bored you by saying it was the 11th of February 2011, I can put it down to almost a day. So why the hell would an object the size of the sun show such a catastrophic change on such a short time scale? So the sun's magnetic field changes on a sixpence, right? It goes into a different mode. Here's another look at it. So this is just zooming in on the February 2011 kind of change. You see that there's pretty much nothing after at the equator. One of the weird things about buoyancy and pressure balance and all these kind of things is that you're always going to have local hotspots or local places. Sunspots are all about buoyancy, right? Where if you think about it, you've got this kind of submarine sitting at the bottom of the ocean, and you change the ballast and the thing raises buoyantly, right? So sunspots are really manifesting the change in the pressure balance on the inside of the sun. When you've got no imbalance, you get no spots. When you have lots of imbalance, you get lots of spots. So I'll go into this. This is just to fry your brains. This is now longitude as a function of time at a set of latitudes. So the northern hemispheric activity belt, the equator again, and the southern hemispheric activity belt back in 2011 again. The idea here is to show that not only is this a latitudinal effect, but it's also a longitudinal effect, right? So whatever happens, it propagates around the sun in the matter of a couple of rotations. So 50, 60 days. Wow. Sorry, my sidekicks are arriving back in the house now, so I apologize for any background noise. Shh. It's no one you know. See?
Okay.
You're famous on YouTube now. All right? No, I'm kidding. All right. What you've been wanting your whole life. All right. Okay. So these Terminator events seem very superficial, but they're really not. Okay. They're indicators that the sun has a magnetic Hale cycle. So the sun's magnetic cycle that repeats over and over and over again.
Right.
It seems to start at high latitudes. They migrate to the equator, but that time of migration is pretty variable. And it's the variability in the progression to the equator that messes around with why some sunspot cycles are 8 years and some are 14 years. We can get into that conversation a little bit later on. There's some really fascinating stuff in that. But what we basically identified is it helps us to shape or understand the shape of the sunspot cycle. So, working in a field where it's highly competitive, everyone's intrinsically skeptical. Okay? So in the data, so we analyzed data going back to 1860. So back to the very first H alpha images of the sun, the first applications of the Balmer alpha line photographically taking plates of the sun. And you can clearly see the terminator events. You can clearly see the polar crown filament. You can clearly see a host of things. But that 14 of these events is not good enough for my colleagues. Okay? 14. Not 1, not 2, 14, not a fluke. Well, they challenged us to find an algorithmic approach to identifying terminators. And that's what this is. So are any of you familiar with the Hilbert transform?
Read about it.
You're familiar with a Fourier transform?
Yes.
Not a furry transform, a Fourier transform. Sorry, you go away now. Go on. All right. A Hilbert transform is very much like a Fourier transform, except when the time series is not stationary. So in other words, the phase of the time series is shifting, right? So if the phase in the time series was stationary, I could apply a Fourier transform and understand this stuff, or characterize it in the terms of sine functions. The problem is the sunspot cycle is not stationary. And so you shouldn't use Fourier transforms to analyze it. My apologies to anyone on this call that has done, but you shouldn't, really, mathematically, right? You use a Hilbert transform. And when you do a Hilbert transform of that time series, which is in the top, there, the red curve, I detrend it. I won't talk about detrending. It's fairly simple. You get left with an oscillatory pattern that's in panel B. The output of the Hilbert transform is an amplitude function, so how the amplitude of your signal varies with time, but also how the phase of the signal varies with time. Okay, so the phase function is a new thing because I've used the Hilbert transform. And it does a really, really, really curious thing. The Hilbert transform, if you have one of these, is constantly being deployed on your watch, right? Why is it doing that? Well, it's looking for heart arrhythmias, right? So it's looking for the highest rate of change of a signal. Okay. When you get to an event like the terminator, you're looking for the rapid rate of change of the sunspot number. And guess what? That's identically when the phase function of the Hilbert transform wraps around. Okay, so those yellow diamonds in the lower part of that plot were my 14 events that my colleagues don't believe. The phase function crossing through 0 at that time is an indicator that even a dumb mathematician can get it right 14 times, right? In fact, more than that, you can go back to the very start of the observational record of sunspots now. So go back another 140 years. So you now have all 24 cycles. So this is actually what happened the day that the panel met to talk about cycle 25. Okay, so we did a little numerical experiment for ourselves. Our hunch, because of this idea of overlapping Hale cycles and the fact that the magnetic fields interact, what we were basically saying is that the sunspot cycle, the separation of the terminators, was an indicator of how strong the next sunspot cycle was going to be. Because if you're kind of worried about how long that minimum time is going to be when everything's overlapping. So we directly compare the time between the two Terminator events using our Hilbert transform technique, and then comparing them to the upcoming cycle strength. So if I just take the first numerical experiment and look at my intermediate cycle strength, I get zero predictability, right? So all outcomes are equally possible. However, if I look at my Terminator separation against the upcoming field strength, I get something kind of cool and maybe powerful, right? So this literally happened the day that the panel was meeting to talk about cycle 25. So what we were basically looking at is the magenta dot here is the Sunspot cycle 25 prediction panel's guess. Based on our analysis at the time, we were looking at a Terminator date sometime a year later, which meant that the Terminator separation would be about 9.5 years, which means that we were totally a factor of 2 off, right? So our forecast was a factor of 2 greater than the one they were talking about down the stairs. Maybe not sound like much, but I don't know. We'll get to that in a minute. So what can we do? So in the space of 10 years, we've learned to observe the progression of hail cycles. We can do it with magnetic fields now. Haven't showed any of that. So magnetograms. So those beautiful blue and yellow movies that I showed earlier, we can now use those to trace the presence of hail cycles. Right. The data absolutely 100% supports the concept that hail cycles interact with one another, and as a result, shape the production of sunspots. That's a big problem. Using the key feature of the hail cycles, so their death, right, this termination event, their end point, they have a definitive end day. In fact, there's an established relationship between the upcoming cycle strength and the separation between those events. So at the time, we were projecting something near 200 sunspots, right? So this is at the time. So this is May of 2019. And then we get a little bit cocky, right? You know, like, well, if this is right, then everything you see is bullshit, right? Everything that's in the textbooks is bullshit.
Yeah, you're the outlier.
Right? And I'm the outlier, right?
Yeah,
so
you guys the outlier,
right? Yeah. So I guess we got brave, right? So because there's a trick to this, right? And you can forecast. What I haven't showed in this is you can go back and reconstruct the time series. Right. You can go back and using the Terminator separations, show how well you would recover the previous cycles. And we were accurate to some like 87%, right? Going back over 300 years.
And would it be right, Scott, that there's no other models even get close to that, right? Nobody going backwards, right? There's
no, well, they go backwards well because you tune them to go backwards well. Right. So the problem is it's when you let them play forwards. It's kind of like a weather forecast, Carl. Right.
Okay.
You can hindcast the weather really well.
Yeah, I guess.
But it's when you stop the forecast and let physics take over is when it starts to deep. That's why a weather forecast 24 hours from now isn't too bad, but at 48 and 72 hours, it's getting progressively worse. Yep. Right. So it's the same thing, but with a star, right? So we had put our collective genitalia on a slate, okay? I guess that's a clean way of putting it for YouTube. And so the challenge was, when would the Terminator arrive? And I apologize for the gratuitous graphics, right? It was just too good an opportunity. Well, finally, after a year of waiting and watching the thing die several times, the Terminator arrived on the 13th of December, 2021. Right? Again, I could tell because things change fast. Right? Again, you see the preclusion of stuff, you see stuff, you see stuff, you see almost no stuff. right? I'm using technical terms to describe stuff, right?
Yeah, but it's clear.
Right? And this is the data as actually up to, it says 11/26, so last week. Okay? So that equatorial things like a void. But these bands from the mid-latitudes are converging on it. So you start to see signatures, and eventually it'll converge just like the other one, cycle 24 bands that you see dying. So yes, this will happen again. If I look at it on a slightly longer timescales, you now start to see more of the definition of the terminator event and the spring up of mid-latitude activity. So again, this event's no fluke, right? The sun's doing what it has done many times before. If I look at it, there it is up until today. So no big change. Yeah, who cares? Okay. Here's the even longer time scale. So this is going back to the record that I started when I was a postdoc, right? So the older data is a wee bit ratty because I said it was only 100 images a day. Of those 100, I only really used 4. And you can see that there it is. You can see the 3 terminator events clearly in the record. You can see massive overlap of bands at the equator.
Oh.
And you can see the fact that activity springs to life at mid-latitudes. Yeah, this is still not believed, right? Don't need to get into this. This is just an animation showing how it goes from having multiple peaks to flattening out to springing up with multiple peaks again. It's just a scan through the data set. It's nothing really graphic here. It was just a diagnostic that we used to try and figure out when the bands were starting to strengthen again. Kind of cool. Back to my longitude plots. At some point, I'll explain why these are important. But remember that the bumps and wiggles in the sunspot, in the hemispheric sunspot record, how it had wiggles in it? And I said that those wiggles are to do with what we call Rossby waves. Well, Rossby waves are planetary scale waves in the Earth's atmosphere that determine weather. These trains of things that are tracking through this middle plot right here are a definitive signature of Rossby waves in the sun's interior, right? If I was to sit over your place and build the same kind of map for the cloud cover, you would see trains of clouds as the pressure fronts come in, right? Okay. So it's no different. The sun just makes spots instead of clouds, right? Mm-hmm. Here's the contemporary one. So this is it. Can you see the terminator in this data? Look at the middle plot. Right there in the middle. When does the equator go dark? Do you see it? There's something also very devious in this plot. If you look at the left and the right hand panels and look at September 2016, the opposite happens. Do you see how it seems like sunspots just turn off? Why? They just stop. Activity just stops. In fact, there's only one X flare between September 2016 and December of 2021. And you can probably spot it in there. And anyway, if you have eagle eyes. So there's again the contemporary data. So you can start to see the fact that the bands at low latitudes are starting to impinge on the equatorial region, but now you're starting to see these trains of features come. So basically what that means is when you look at a sunspot on one rotation, if it covers one entire rotation, it won't be exactly at that longitude again. It's slightly prograde. So the sunspot is actually moving slightly faster than the surface rotation.
Moving forward.
Yeah. So it's anchored at a place that's moving faster than the surface. Right? And so you can use that to do all kinds of diagnostics of the internal plasma characteristics. Just like we do for the Earth, right? So
What?
anyway,
Where's the ink?
okay, because for the Earth, the trick is, right, so Rossby wave thing, there's a set number of peaks and troughs in a Rossby wave as you go around the Earth, right? Low and high pressures, right? And if you can understand or use global observations to measure that, you can predict how the system's going to evolve over the next couple of months.
Right.
Same thing for the sun, right? So you know where all the magnetic field's going to come out, because it only comes out in high pressure places. Yeah, so a little glimpse of the future here. Okay. But the challenge for us was, okay, when is this bloody Terminator going to happen? And what's it going to do to our forecast? Right? Because the last thing we wanted to do was for it to drag on for another 2.5 years so that we could no longer confront the magenta dot, right? So we were wrong. And then there's a good reasons why we were wrong in 2019 forecasting a 2020 Terminator. We've subsequently learned a lot, right? But that means that we had to revise our forecast because we still believe that the physics is right. So we waited for the Terminator to come, and it happened on December 13th of 2021, which meant that the Terminator separation was actually pretty close to average. The average over all 24 cycles is 10.86 years. This one was 10.72. So it was very boring. And as a result, if you look at the big M, see that subtle big M in the plot? That's the mean, right? And that also means it's a mean amplitude cycle. So instead of being one of the top 5 of all time, which it would have been, it's now looking like a boring average. Yet the boring average is still 75% greater than the predicted value. Okay. So what happens to the sun when the Terminator happens? Do any of you know about cosmic rays? And the fact that the sun's magnetic field is like a big magnetic umbrella to protect us from cosmic rays? Well, when the Terminator happens, the sun's magnetic field reacts instantly and goes, which blocks the number of cosmic rays that hits the Earth. Can you see the change?
Yeah, big drop.
Pretty dramatic.
Big drop.
Big drop, right? Consistent big drop. This is a 10% change, right? Actually, one of the things that we're starting to look at now in terms of things like climate and sun's effect on weather and climate is that the cosmic ray flux may have a very significant role to play, right? But rather than photons, because the photons don't change all that much. So a couple of cheesy movies, because I'm a solar physicist, I get to play with very expensive toys and make movies out of them. So here's a couple of gratuitous movies, basically just showing the early phases of cycle 25. So when it wraps back around to the start, let's see if I put it back there. The sun's not completely quiet, but it's pretty quiet. But pretty soon it springs to life. It's not quite as, actually the initial phases are not quite as dramatic as they were back in 2011, but cycle 24 ended up being a wiener. So we can talk about that one too. So we get into the part of the talk where we're talking about progression. And so some of these plots are about a year old, but I've updated them today. Let's see how this works. Okay. So as of 2023, February of 2023, we're on the money, right? Absolutely categorically on the money. Sun is almost like we wrote the script, right? It never really works out that way. But the other thing that we're tracking is, when does solar maximum happen? And so in a lot of our devious cantankerous messing around with data, we found a whole bunch of other things too. But it turns out that these Terminator events and the Hale cycle are very important for timing. right? So it's almost like the sun's clock, right? If you can understand when those events happen, it turns out that a lot of solar phenomenology and anything related to that, like flares and CMEs, and well, they can be translated back onto that same. It's kind of like you modify time. So in like the Earth has a very regular clock because it takes 364 and a quarter days to go around the sun, right?
Yeah.
The clock for the sun is the Hale cycle. So if you take all of your solar diagnostics and map them onto the Hale cycle, so a Hale cycle from start to end is your unit 1, you start to see that things on the sun are not arbitrary and they start to statistically behave with one another, right? Right. So you actually can do climatology of the sun once you understand what the basic time unit of the sun is, right? That sounds a wee bit hairy-fairy. But this plot just basically shows us what one of the things that we're waiting for is the polar reversal, right? So when the sun's polar magnetic fields reverse, that is solar maximum. So focus your attention on this panel B here. Panel B is from the Wilcox Solar Observatory out at Stanford. And you can see this beautiful progression where the opposite polarities go in and they cross through zero and they come back out and they cross through zero again. This is a manifestation of the sun's magnetic field flipping signs. For context, the Earth does this every 200,000 years. Right? The sun likes to do it every 11. Right? Whatever. Right? Whatever. Anyway, but what we're looking for is the time at which the magnetic field crosses through zero is telling us when solar max is going to happen. Now, the other thing that was bad about the NOAA forecast was that they put solar maximum in the middle of 2025, right? So not only did they get the amplitude wrong, it looks like they get the timing wrong too. Because if we started to look at our data and say, okay, if we think we know how this system works, we can actually use this to forecast when the polar reversal is going to happen. So actually that future data, do you see in the panel B, there's actually future data. We've gone out into the future.
Yeah. And
also in panel C and panel D are because we think we understand statistically how the sun behaves, right? So there's this mad trick called a superposed epoch analysis that you can use. Again, it's another meteorological trick. And so if I look at the data today, it's actually followed that future path pretty damn well. I know that this is only a short time frame. This is only 2 years. That's what I hear. It only followed it for 2 years. I'd like to see you follow it for 2 weeks, dude. Right? Far less 2 years. So sunspot maximum is pretty much upon us. I think we've got nothing much more than 6 to 9 months, maybe. We might get a double peak. We might not. We might have already reached max. You can already see that it's bigger than cycle 24.
Yes.
Right?
Yep.
So we're already there. Because I work with the ham radio community a lot, they love F10.7. Do you know what F10.7 is?
Solar flux.
The solar flux, right? And so they're like, can you use your mad superposed epoch analysis to look forward, right? Okay, so I said, yeah, that's a challenge. I think we can, because there's a very distinct correlation between the solar flux and the sunspot number. So we set about reconstruct using the 1947 when it started?
Go back.
The solar flux record, and using the superposed epoch analysis to look statistically what it would look like. So that's the green cloud here. So this is scaled by sunspot, so it's scaled by our predicted amplitude, right? But the envelope in time is all to do with statistics. So we're assuming that in the fall of 2032, there'll be another terminator. And so that changes that side of the plot. So if the terminator comes early, that black vertical line comes in the way. But if it goes that way, then things flatten out, right? So this is just the basic idea. Okay, so how do you think we do? You ready?
Pretty good.
This is a sequence of plots. So there it is. There it keeps going. There it keeps going again. In fact, this is like the peak of activity. Oh, look, it turns down again. And this is as of today. So we were baffled when we looked at the statistical average that they had this weird double peak structure, right? We did not anticipate that. But maybe just the sun is replicating that behavior. This isn't fudged. If you follow me on Twitter, you can see the monthly versions of this since we started doing it, right? So the sun is kind of following the prescription. Kind of. Not great. But the other thing that the solar radial flux gives you is an understanding of how the Earth's thermosphere or ionosphere is reacting. So if you just happen to be flying satellites in low Earth orbit, this is a very, very important measurement for you because it changes the drag on your spacecraft. So if you use a prediction, and I'm bound by NDAs, so I can't say who did, right? If you use a prediction where the amplitude of the sunspot cycle was almost a factor of 2 lower to drive your understanding of drag and the thermospheric density, you have a lot of satellites in the soup.
Yeah, that happened this year, didn't it?
There's lots. That's Boku cash, right?
Yeah.
Anyway, so who says that astronomy and solar physics doesn't have a real world implication, right? Anyway,
it does.
So this is what F10.7 is doing. We thought that this was a kind of fun trick. How's it doing relative to my earlier plot? All right, so we had to revise the amplitude, right? There's the new red plot. Remember how I said it was close to the average, which is the green plot. It's still outperforming the NOAA NASA forecast.
By a lot.
Okay, and in fact, about 4 weeks ago, they changed their website. So their forecast now looks a lot more like ours. Okay. So it's interesting. It's academia. Nobody's going to give a shit. And right about 2032, there's going to be a cycle 26 prediction panel. And all of this will be forgotten because the models will be new and improved. Okay. Does that sound skeptical? So this is where it gets a wee bit interesting, I guess. So as of today, this is what the sunspot record looked like. So remember how I showed you earlier on, it's deviating from the blue lines. And it was tracking beautifully. Well, for about 2 or 3 months now, it went off a cliff.
Right.
And this last few weeks, it's starting to look like it's perking back up again. And this is the longitudinal stuff kicking in. So now see how those kind of very pronounced peaks, right? You're now starting to see the wobbles. So as the sun becomes more active, it's almost like tidal, right? The sun surges and then retreats, and it surges and retreats. So we're now looks like we're in the rise phase of another surge, right? So that would be my prediction that over the next 6 months, this thing's going to get wild. Right?
Yeah, pick up a little bit more.
Yeah, a wee bit. It's going to push it back up close to that red curve again.
Yeah.
And that will take us to solar maximum probably sometime in the middle of the year. And then we're waiting for the fall of 2027. Because that's when shit sort of switches off again. Right? So, and it's very weird. I'm going to jump back real fast because this is fascinating stuff. Actually, I mean, it's maybe really boring, but to me, it's really fascinating. Because the Terminator event is really cool. Very pronounced.
Right.
But the switch off is also wild. Right? So let's say you're preparing to launch a spacecraft to Mars. Right? There's always the list of, am I more worried about cosmic rays or am I worried about CMEs and flares? Right? Because they're kind of out of phase with one another. So there's a calculus in trying to figure out, okay, the poor buggers that are in that spaceship, what's the best radiation to expose them to? Or how much shielding do I need, and how much do I need to dig into the Martian regolith or whatnot? Well, likewise, if you're preparing a mission to go look for flares on the sun, do you want to launch it in the 2028 timeframe? Bearing in mind that it might not see a flare till 2033.
That makes sense.
Right?
Yeah.
Well, these are $500 million spacecraft. Right? So we fully anticipate. So and it's very weird, the sunspot record. Why did I come back here? Well, what happens is sunspot production basically switches off. Right? You can see how it kind of dips away. It actually is worse than that for flares and CMEs. So it turns out that flares and CMEs are all about complexity in the magnetic field. And this whole thing that I showed you about longitude, we're still kind of piecing this together. But see how the characteristics, so if you look at this left-hand panel again, there's a dashed line in September of 2016. And basically the sun goes quiet at that point. They still make some spots because there's still this longitudinal imbalance going on, but it doesn't make any big flares anymore, even though there's spots there, right? So there's this something weird is going on with the arrangement of the magnetic fields that says, okay, I can't be complex anymore. And it basically starts the decline into solar minimum. And we're just puzzled by this. But again, it seems like it's another strong indicator that the magnetic fields on the inside of our star know about one another. Right? It's like there's a real connection. So, we're watching very carefully because our modeling allows us to say with pretty good resolution when that's going to happen for cycle 25. Right? To within 6 months, which I would say is pretty damn good. Right? And if you're planning a mission that's a $500 million mission and when you're going to launch it, that's a pretty useful piece of information for you.
Yeah, it is.
So anyway, that's a big aside. To me, the switching off of activity is almost more conclusive that the magnetic fields are playing with one another than the Terminator. The Terminator event's very obvious compared to that. I'm not explaining this very well. But basically what happens is do you see how when these bands, so if you look at this plot, for example, and look at in the 2004 timeframe, there's a period of time when the two bands in each hemisphere are very close to one another.
Yes.
And we think that it's the interaction of those that turns down the production of complex activity, right? So that when that system crosses 45 degrees, when the higher latitude system crosses 45 degrees, you basically get no spots. You get spots, but no flares, no CMEs. So anyway, sorry, I'm making everyone sick by jumping back and forward. So I've completely lost track of time. So that's it. The sun has a fundamental mode. Looks very much like the magnetic field is the fundamental mode. So there's the magnetic polarity cycle or the Hale cycle after George Ellery Hale. The Terminator event seems to be not only a kind of singular and spectacular event in terms of the sun's magnetic field, but it seems to be a trigger for things changing globally on our star, and it happens real fast. We're still watching to see if cycle 25 is going to be single or double peaked. That's another interesting story.
And the double
Right.
peak's kind of a typical thing, isn't it, Scott?
It's more typical than not.
Okay.
Invariably, the two hemispheres of the star are not synchronized.
Have you discussed, because one of the things that we've presented, or just to touch on, and I've raised more questions, is when we said when you look at cycle 24, I thought that it was unique. Correct me if I'm
It's
wrong, but
way out of whack.
yeah, that the second peak was a little taller, and a lot of papers said that was unusual. And what does that
Yeah,
tell?
and also separated by 2 years almost.
Oh, is that separation shorter, or?
It's a massive separation.
Oh, okay.
But there may be a reason for that. So I don't think I have. Let me see. I'm going to make you sick again, right? There's a telltale sign in the Hilbert transform of something really weird with cycle 24. Let's see. I don't have good resolution on it in here. Something happens in the fall of 2003. What happened in the fall of 2003? Do you remember the Halloween storms?
Yes, they were huge,
Those were in the southern hemisphere. I can't remember which hemisphere they were in, actually.
but they were big.
Got to be. They were massive.
They were
The
big.
biggest we'd seen in 30 or 40 years.
Right.
Right. The question we are trying to address in a paper right now, because if I showed you the Hilbert transform data at a slightly higher resolution, I don't want to try and find it right now. The phase spectrum goes like this. Straight line. Actually, well, I'll try and copy the one that's in the plot right now, right? Well, if you look at it in higher resolution, it goes from that angle to that angle in the fall of 2003.
Okay.
So what that basically means is now where the zero crossing of my phase spectrum just shifted out 3 years. Right. So if remember, I'm saying that the zero crossing point here is the estimate of the terminator.
Yeah.
Well, in 2003, that it was progressing lovely towards the equator, and then went pink. It took a right turn.
Why?
We think it's because there was so much magnetic field destroyed in those storms. Right. So there was so much field destroyed in those storms that it basically slowed down cycle 24. Right? So actually what it does, it slowed down 23, but then 23 ate into 24. Right? Do you know what I mean? So if I go here, look at the separation time frame for cycle 24. It's 13 years. There's only been 2 bigger than that. And those are tiny little cycles. Right?
Isn't it the shorter that separation, doesn't that tend to
the bigger the amplitude?
That's what I thought.
So the longer, the more stretched out it is. And where the space to see that is in here. So if you look back at the Dalton minimum at 1800,
right?
See the grand minimum there? Look how separated the terminators are.
Oh.
Do you see that? But in the activity maximum of 1950, how they all pinch in together. And the amazing thing through all of this, Carl, is that high latitude thing that's going on at 55 degrees is still going at 21.8 years.
So
right? Sorry, go on.
I say, do your studies, do they suggest that cycle 26 will be weak and, just continue this
average?
Average. Okay.
So right now, when we see cycle 26 pretty soon, maybe a year from now,
Yes.
we'll be able to tell, right? We'll be able to get my now, that she'll be 17 at that time, to draw a straight line on it, right? So when we see the trail of breadcrumbs of at 55 degrees, we should be able to put a line on it and figure out roughly where it's going to cross the equator,
Okay.
right? So that what all that means is we'll understand the relative phasing between cycle 24 and 25 and 26.
To 26.
Yep. So yeah, but this, hold on, sorry, again, I should organize these better, I guess.
This is great.
This is based on an average terminator separation.
And this
Right,
is the
so-
forward- this is the forward look.
Yeah. So this is, if I take remember I said it was like 10.87 years or something like that.
Yeah. Average.
If I take that and add it on to December 13th, 2021, this is what I get,
That's what you wrote.
right? So I can play with that. So the idea is that as we start to see 26, I can now play with the tail end of this plot.
So the Terminator research suggests that the cycle 26 will not be non-existent.
Right. So this whole idea of a grand solar minimum is probably bunk.
So we're not there yet.
No, but you can ask the question of how you would get there,
Oh, do we?
right? Because persistent solar minimum,
Yes.
what does that look like? So in this paradigm, it means that you have almost constant cancellation between the bands of the Hale cycle.
Yeah. What makes it go away?
Asymmetry, right? So eventually, if you think about it, if my clock at high latitudes is running at 21.8 years, you can go through a set number of cycles and you'll have a third system present. So let's say you completely ground to a halt, right? And the thing is just canceling. It's just permanent solar minimum conditions.
Yes. Like
You'd go through several cycles like that. But eventually, because the high latitudes are just doing what the high latitudes do, it throws in a third system, which would give you asymmetry, which would break the cancellation. And then you go back to,
starts
because
over.
it's kind of funky. It goes back to start again. The question is, how do you get into that? So this is why we're looking for, in the ice core samples, and why we're looking for low latitude aurorae, right? Because what we're trying to understand was things like the Maunder minimum triggered by very extreme activity, right?
Okay.
We're actually thinking that it may have been very extreme activity that started it. Because you ate up so much magnetic field, you basically ground the system to a halt. So you wouldn't find that in ice cores. You'd find that in, Hawaii and lower latitude phenomena. Because you're looking for mega storms.
Okay.
Anyway, just speculative nonsense that's now on YouTube.
Yeah, there's lots of it out there.
This totally fits in.
That's
So, but
pretty-
I don't see any indication that 26 yet would be any lower than 25.
so another average.
I would
Confident.
guess average is a good place to start.
Hey, can't go wrong with that. So
Yeah. So, but that tells you a lot about the physics too. It's like, this is what the sun really wants to do. It wants to be average. And somehow the way the machine speeds up and slows down gives rise to bit highs and lows.
yes.
Right? And it's just oscillating around an average. Boring. What a boring star.
Well, that's okay because if it were to, I mean, I kind of have argued that if it were to fall off into an extended solar minimum, that creates problems here. I believe it would create problems here.
A lot of cosmic rays.
Yeah, lots of cosmic rays and all the things, all the associated things that go along with that. And what does that mean?
Yeah, and we don't know how the Earth's atmosphere will respond.
Yes, I
Right.
believe that's a huge area of study and debate. That
Yeah, we don't know how. I don't think we know how the Earth's atmosphere would respond to that.
extraordinarily complex. So
It's not simple, that's for sure.
yeah,
Or someone would have nailed that already.
yes, yes.
But I think a lot of people in my field would love that experiment to run, but I'm not sure I would.
No,
I mean, the real life experiment.
Yeah, I'm with you there. I kind of like the nice temperate climate myself. So
I like the boring average sun.
Yeah, the boring average is probably good. Another argument that people have made in our group is that, you know, myself being included, isn't our own umbrella, to use your term, you know, around us is kind of changing, you know, and weakening. And so what does that mean for us and relative to this? And so it all kind of stacks up on each other. And so,
yeah, it's fascinating interaction dance between the sun's magnetic field and the Earth's.
yes.
Right, because often when I give a lot of public talks, I start with a movie that shows, you know, we live in the atmosphere of our star, right? You know, the atmosphere of our star goes out beyond Pluto.
Absolutely.
So, but most people don't really think of it that way. They think space is a void, and it's no. That is the atmosphere of our star, and we're just embedded right in the middle of it.
We live in it. We live in it.
Yep, we live in it. So, thank goodness we have a magnetic field.
Yes, I agree. But
the Martians weren't so lucky.
No, something went wrong there. Something went wrong.
Yeah.
Something went wrong. But I appreciate your time tonight, Scott. This is probably one of the best presentations I can think of that is on this subject. It's never gone this deep, or to have somebody of your caliber to share your research. I really do, on behalf of CAA and everything. And thank you for giving up a chunk of your Friday night for us. I really appreciate that. And so I'm sure on
I
behalf
think it
of
might be
everybody
time
else,
if anybody has a question, feel free to unmute and ask the question, or go ahead and put it in the chat.
I have a question.
Sure, go ahead.
Thank you. Well, I had a lot of the presentation tonight. I did.
Thank you.
Sure. But my actual question is, I heard that you're into math. Is that correct?
No, I hate math.
Excuse me. Come on. That's not what I was looking for. But I heard that.
You know, I vector calculus is my jam.
Okay, well, I had heard that's kind of right in your field, because that's what I was told. But I had to ask, and I don't know if I could. I don't know if I could ask this question, but and I don't feel silly to ask this question. I have a roommate, and her dad is actually a math teacher, and I didn't know how could you, Scott, could do anything around to what you did tonight around your field. And I'm wondering, how can you do that?
You do need math, unfortunately. You need lots of math, unfortunately. So, and that's one of the big drawbacks of. I think that's one of the big drawbacks of entry into this stuff. You know, I've spent the last 5 years trying to convert meteorologists into solar physicists.
Mm-hmm.
Right?
how's that going?
And do you know what their challenge is? When they
Probably,
see electricity and magnetism in school, they run a mile.
Yeah.
Right.
yeah, probably more than I
Right.
know, maybe.
Yeah, maybe several hundred miles.
Well, hey, thank you, Scott. I appreciate that.
No problem. Good luck with your math teacher roommate buddy.
I don't know about that, but thanks.
Awesome.
There is a couple of questions, or there's one question in the chat here. Seems like we haven't had as many X flares so far in this cycle. Is that true?
Well, when I had to give I'm trying to find a talk that I gave in Washington in the spring. Hold on. I actually looked at this. Here we go. All right, can I reshare for a second?
Sure, yeah, go ahead.
All right, I actually looked at this because let's see if it'll allow me to share my screen. Here you go. So I gave a talk to the space weather, the primary government federal space weather people near the White House in, I guess it was in March. So you've seen some of these plots again, talking about stuff, lots of stuff. So as of the time of writing, there was 17 X flares since the Terminator event, and that was 40% more than cycle 24.
Wow.
Similarly, let's see if I did this for M class flares too. Oh, so here's the slide with the statistics. So I think we're like 200% more M class flares than the past cycle.
Wow.
And I think that's got even worse. So there's not been a huge number of X class flares, but there's been bajillions of M class flares. And what's really pissed off a lot of people in my field is they seem to happen right as the spot is crossing the limb. Right? So they're happening just behind the limb.
Yes.
And so if you're measuring an M7 flare just behind the limb, then every likelihood that it was an X-class flare. Right? And this is actually one of the reasons why a lot of us want to build a constellation observatory for the sun. Yeah. Right? Not just, it's actually to study the weather of the star. Right? The stuff I was rambling on about longitude. People roll their eyes when they hear me starting to talk about longitude. Right, that's my thing. That's my if I had a word, it would be longitude. So yeah, no, there's all kinds of stuff and like strange graphics in here, but yeah, no, that was absolutely. It appears that way, but that's not the case. Statistically, it's higher than the last one. It's kind of on a par with cycle 20 and 21, I believe, which were average.
Still within the average.
They were average. They're just not as boring as cycle 24.
Yeah. That's pretty cool.
So I was trying to, yeah, I know this is, I had a little bit of fun with this talk. There's not many times you can go to Washington and have fun with a talk.
Any other questions? You can go ahead and unmute. You can turn on your camera if you want.
I'm surprised most of you aren't comatose. They're like just asleep.
This is excellent.
So.
No, it's so cool to get your perspective on this. I think there's a lot of different people that they're still here. They're still here.
Yeah, I loved it.
Yeah, you can invite me back in 3 years and you can slate me for being wrong. How about that? I'm okay. I'm okay with being wrong.
So yes,
I'm interested in you presenting again December of 2024 and telling us more about what you found in the ice cores.
I'll do that, but I'll also tell you about what cycle 26 is going to look like. We're going to mark the calendar now.
Really cool. That would be really cool. I would sign up for that.
Yeah, okay. I'll change my name to Nostradamus.
No, I know you're not.
We like that.
I mean, seriously, there's probably a futures market out there that we could tap into.
Probably a little risky, but probably.
Yeah. Well, I think I'll be looking at the risk environment to help them with their risk.
Yes.
So
we'll get the Scotch will be a little older then. So
that's right.
Yes, right. It's only 12 years old tonight. So in honor of you. So, but
thanks you.
On behalf of CAA, thanks again, Scott. I really appreciate your time tonight.
Yes.
And this was excellent. It just is amazing to hear and get this level of perspective. I just find it, and I think as evidenced by the folks that are still signed in here, it's really fascinating, and you do a wonderful job of bringing it down to where, it's very approachable. The way you talk about it and your background, you just make it very approachable. It's very, very cool.
Oh, someone remembered this. Someone remembered the question.
You-
Do you see it?
Yeah.
Oh yeah.
Okay. Yes.
Jupiter.
Yeah, Jupiter. I think this is all the planets. All right. So, probably not is the word. Real. So tidal forces are real because we have tides in the Earth from the moon. It's probably unclear that the gas giants have enough mass because it's not really about affecting the sun, it's about affecting the magnetic field, right? So the processes by which they would have to affect the magnetic field or this Hale cycle stuff, I'm not sure. I think the basic thing is that the energy density and the tidal forces are like thousands of times smaller than the Coriolis force, so the rotational forces, right? So the rotation of if you compare the rotation of the star as an energy source to a planet that's 40 AU away or 60 AU away, it's insignificant.
Right.
But there is that weird quirk that the average sunspot cycle is about the orbital period of Jupiter.
Interesting.
But so, I mean, I think if we ever developed a model to understand this stuff, Carl, I wouldn't discount that. I would like to play with whether or not there's a resonance somewhere.
Yeah, it seems
Right.
like it might be. That seems like it would
But
take-
then you might expect resonances with some of the other planets too, and I'm not sure. Certainly Jupiter and Saturn may, right? But when you get in close and Mercury's tiny by comparison, and we're just insignificant.
Yeah. Yes.
So no matter how many billions of people are on the Earth, it's not going to affect the sun.
No.
So
No, we're along for the ride.
yeah, literally.
We're
Let's
along
just
for-
hope we keep our magnetic field. That's all.
That's just it. That'll be a good thing
Mhm.
to keep. It's changing
Yeah.
now. So we're along for the ride. Like you said, it's a grand experiment. And
Yeah, just remember the Martians
yes,
for Martians.
something went wrong. Something.
Yeah, that crustal field just didn't hold out for long enough.
No,
Uh-uh.
not so much. Not so much. So. But
All right, thank you very much. Sorry.
thanks for your time tonight, Scott. We really appreciate it. We look forward to seeing you again next year. We'd love to have you back and share what's new then. So thank you.
Yeah,
so much.
absolutely. I'll look forward to that too, and you can tease the living daylights out of me, okay?
We'll do
And
that.
work on the accent.
So
And you should have closed captioning running because I'm sure there was some really funny stuff comes up.
Oh, I didn't
Trying
do
to-
that.
Trying to translate a Scotsman. No.
yeah, but we're
Yeah.
gonna remember the Celsius when Celsius met Fahrenheit. We will
Yeah.
Right,
remember. Yes.
just remember that the next time you're up even further north than you guys.
Yes.
So-
Yes. It's cold. So
All right, well,
Okay.
take care. Have a great winter. I hope that the Northern Lights behave themselves and give you some dancing lights
Hopefully
in your
some
cameras.
tonight. Yeah. I'm
thank you.
getting ready to head out. So
All right,
Thank you,
everybody.
Scott.
Good night,
Bye.
everybody.
Be
good
safe.
night.
Thank you.
Thank you too,
Cheers.
Carl.
Holidays.
Cheers.